Hello, everyone, and welcome to my final presentation for EE432 Advanced Computer Vision. My name is Mo. I'm a graduate student majoring in electrical engineering. Today, I'm excited to share my literature survey titled Efficient Neural 3D Scene Representation, a survey from NeRF to Gaussian splatting on edge devices. Here are the contents. My presentation today will focus on introduction, goal, tasks, and challenges, three main approaches, comparative analysis, future directions, and conclusion. Over the past few years, we have witnessed a massive paradigm shift in computer vision and computer graphics. We moved from classical geometry-based reconstruction to continuous volumetric representations like neural radiance fields or NeRF. More recently, explicit representations like 3D Gaussian splatting have emerged, dramatically improving rendering efficiency while maintaining photorealistic visual fidelity. However, a fundamental question remains: how do we bring these incredible high-fidelity 3D scenes out of the lab and into the real world? In class, we primarily studied these models running on powerful desktop GPUs, but in real-world applications such as autonomous driving platforms like the NVIDIA Drive Orin wearable AR or VR headsets, and mobile robotics, we face strict hardware constraints. You might ask, why not just process everything in the cloud? The reality is, for safety-critical or immersive applications, relying on the cloud introduces unpredictable network latency, demands massive wireless bandwidth, and raises severe privacy concerns. We must deploy these models directly on local power-constrained edge chips. When we deploy on the edge, we immediately run into two distinct hardware bottlenecks depending on the representation we use. First, let's look at implicit representations like vanilla NeRF. NeRF models continuous scenes using a multi-layer perceptron, or MLP. Rendering a single pixel requires a volumetric ray marching process, sampling hundreds of points along each camera ray and querying the MLP for every single point. This massive number of network evaluations makes NER highly compute-bound. The millions of floating point operations quickly exceed the thermal and power limits of mobile system on chips, resulting in very low frame rates. On the other hand, explicit representations like 3D Gaussian splatting completely bypass this compute bottleneck. Instead of a black box MLP, 3D GS models the scene with millions of explicit 3D Gaussian primitives, using a tile-based differentiable rasterization pipeline for fast alpha blending. However, this introduces a new problem. Each Gaussian stores high-precision 32-bit floating point attributes, including its 3D position, covariance metrics, opacity, and spherical harmonics coefficients. Fetching this massive amount of data creates a severe memory bandwidth bottleneck, making 3D-GS highly memory-bound and prone to out-of-memory crashes on mobile devices. To solve these dual challenges, my survey categorizes current research into three major optimization directions: optimizing implicit models, optimizing explicit models, and hardware-software co-design. Let's explore the typical approaches within each. The first major task is compressing implicit models. The fundamental difficulty here is reducing the reliance on massive MLP queries without losing image quality. A high effective approach is grid-based baking. A representative A representative method here is mobile NeRF, published by Chen etc. at CVPR 2023. The basic idea of mobile NeRF is to translate the continuous neural representation into a discrete set of textured polygon meshes. The primary advantage of this approach is that it brilliantly exploits the highly optimized Z-buffer rasterization hardware that is natively present on standard mobile GPUs. By replacing heavy volumetric integration with standard mesh rasterization and a lightweight fragment shader, it achieves interactive frame rates on standard smartphones. However, we must also acknowledge its limitation. Baking often trades computation time for exorbitant memory consumption. A densely baked feature volume can easily consume gigabytes of VRAM, exceeding the physical capacity of edge accelerators and creating a new memory wall. Conversely, to compress explicit models like 3D-GS, we must tackle spatial redundancy and reduce the precision bit width. A typical approach is utilizing codebook dictionaries and vector quantization. A prime example is compact 3D-GS, proposed by Li etc. at CVPR 2024. In 3D-GS, the high-dimensional spherical harmonics coefficients often take up to 80% of the total memory. The basic idea of compact 3D-GS is to use k-means clustering to build unified shared codebooks for these colors and scaling factors. The advantage here is a massive reduction in model size. By storing a simple index that points to a shared dictionary instead of full FP32 values, this method achieves extremely high compression ratios, easily shrinking the memory footprint by over 10 times. The limitation to this approach is that reading attributes from a codebook introduces a small decoding delay during the rendering phase. However, this trade-off is absolutely necessary to prevent memory overflows on embedded hardware. Furthermore, structural pruning methods like Gaussian calculate global significance metrics to safely delete redundant primitives that have near zero opacity, directly reducing the sorting overhead on mobile GPUs. However, algorithmic optimizations alone are frequently insufficient to hit real-time targets under harsh thermal constraints. This brings us to the most fundamental optimization: hardware-software co-design. Standard general-purpose GPUs struggle with the irregular memory access paths demanded by neural volume rendering. A cutting-edge approach is designing domain-specific application-specific integrated circuits, or ASICs. For example, the Icarus architecture physically decouples point sampling and neural evaluation into specialized asynchronous hardware pipelines. Even more revolutionary are compute-in-memory, or CIM, paradigms. The von Neumann bottleneck, the energy cost of transporting massive weight matrices from memory to processing elements, is a critical barrier for edge inference. By utilizing non-volatile memory technologies like RRAM, CIM architectures embed computational logic directly within the memory arrays. The defining advantage of CIM is that it fundamentally eradicates data movement overhead, translating to orders of magnitude reductions in energy consumption. The limitation, practically speaking, is the high cost and complexity of fabricating specialized silicon, meaning in the short term, we mostly rely on FPGAs or embedded neural processing units, namely NPUs, for deployment. To put all this into perspective, I have compiled a quantitative comparison matrix evaluating visual quality against strict hardware metrics. Notice the paradigm shift here. Vanilla NeRF maintains a small footprint, but operates at a very low frame rate, often less than 1 FPS on mobile, because it's heavily compute-bound. Vanilla 3D offers excellent visual quality, but crashes with an out-of-memory error on edge hardware because it requires between 4 to 10 GB of VRAM. The sweet spot for edge deployment is distinctly found in compressed, explicit models like light Gaussian. Through pruning and quantization, it reduces the model size to just around 30 MB and keeps VRAM usage comfortably below 1 GB. Most importantly, it achieves over 60 FPS on mobile, making it highly suitable for latency-sensitive applications like mobile AR or VR, where high frame rates are mandatory to prevent user motion sickness. For resource-constrained robotics, frameworks like GSSLAM similarly leverage explicit representations to provide much faster tracking compared to traditional NeRF-based SLAM systems. This brings us to the final part of my presentation. The final project guys ask, how would you improve your result if you had one more month? I would like to say if I had one more month to extend this research, I would focus heavily on on-device training and adaptation. Currently, most edge frameworks are strictly designed for inference. However, a mobile robot navigating an unknown environment faces an unbounded memory growth challenge as it generates new maps. I will deeply analyze online continual learning frameworks like Pocket.js, which demonstrate the feasibility of on-device 3D.js training under strict compute constraints. Looking broader at future research directions, two massive open challenges remain. First is the rendering of dynamic scenes on edge devices. Current compression techniques focus on static environments. Handling real-time, deformable dynamic scenes, often referred to as 4D Gaussian splatting, remains an immense hurdle for memory bandwidth. Exploring temporal smoothness aware rate distortion optimized 4D will be a critical next step. Second is the development of unified hardware accelerators. Algorithmic compressions can only take us so far, but to fundamentally overcome current bottlenecks, the industry needs to design hardware that natively supports explicit operations like rasterization and deep sorting. Architectures like NEO, which propose a reuse and update sorting mechanism, point toward the definitive solution for the 3D.js memory bandwidth crisis. To conclude this survey, it is evident that edge neural rendering is undergoing a massive shift from pure algorithmic improvements to hardware-aware design. While implicit models lay the foundation, explicitly structured representations like 3D Gaussian splatting, augmented with vector quantization and parameter pruning, currently demonstrate the absolute greatest potential for real-world edge deployment. They successfully balance high visual fidelity with strict memory and power constraints. Thank you, Professor Wu, and thank you to everyone watching. for your time and attention today. I hope this presentation offered valuable insights into the intersection of computer vision and edge hardware. Have a great day.